Hi, I'm Arman Afrasyabi from University Laval, and I'm going to present mixture-based feature space learning for few-shot image classification. In few-shot image classification, we aim to predict the class of a given query by having a set of very few examples as a support set. Here we transfer knowledge gained on a set of base categories containing large number of training examples to the set of distinct novel classes having very few examples. Having a closer look at the typical pre-training procedure and giving a batch of base classes to the network learns embeddings and aims at maximizing the distance between these vectors, which are single learnable component per class in a fully connected or FC layer. In this case, the main assumption is that each class can be represented in a unimodal manner. Indeed, Allen et al. Showed that relying on that unimodal assumption limits adaptability and proposed infinite mixture prototypes. However, their model suffers from some limitations. First, they used DP-Mins, which is a classical clustering algorithm, in a non-differentiable way. Second, their model performs temporary clustering inside each batch in an offline manner. In this work, we propose a multi-model method that is fully differentiable, trainable in an end-to-end way, and captures mixture representation without any classical clustering algorithm. Our method is entitled as mixture-based feature space learning, or briefly MixtFSL. In this work, instead of reserving a single learnable component per class, we reserve codebook P containing multiple learnable components per class. Here, the overall goal is representation learning in both between and within classes. Our MixtFSL consists of two training phases, initial training and progressive following. Let's start with initial training stage. For better visualization, we focus on the learnable component for kth class in the feature space presented by red stars. First, network embeds an example of kth class presented by red circle. Then, network projects embedding Zi to the nearest component U star using a loss function called assignment loss. In addition to the assignment loss, we also have diversity loss, which minimizes the distance between Zi and the mean of all components of the kth class. Here we have diversity loss because unfortunately employing only assignment loss causes a single component to dominate while other components became deactivated, shown in the figure with a big clump. Our MixtFSL contains the second training stage or progressive following, which aims at learning more discriminative embeddings. In the progressive following stage, the network is supervised by a fixed copy of best detected target model of the initial training stage shown in blue to stabilize the training. The target network and mixture components are replaced by the best validated network through the time. In this slide, we have the TSD visualization of the learned feature embeddings, circle, and mixture components, diamonds, after initial training and progressive following stages. We evaluate our MixtFSL using 4 datasets and 4 different backbones. In this presentation, we are providing the main highlights, but please refer to the paper for all the details. Here you see the evaluation of our MixtFSL in 1 and 5 shot in mini ImageNet dataset using ResNet 12. Our MixtFSL outperformed the state-of-the-art by 0.47% in 5 shot coded by blue. This table presents similar comparison, this time for tier ImageNet for both ResNet 12 and ResNet 18. In particular, our MixtFSL results in classification gain of 3.53% over the argmax in 1 shot using ResNet 18. We also have the evaluation of our MixtFSL using FC100. Here we have 4.60% over the state-of-the-art in 5 shot. Next, we have the evaluation of our MixtFSL on CUB both for fine-grained classification in 1 and 5 shot and for cross-domain adaptation from mini ImageNet to CUB in 5 shot using ResNet 18. Our method gains 1.74% over the state-of-the-art in cross-domain adaptation. We also adapt our MixtFSL with associative alignment algorithm to extend our work for fine-tuning and evaluate on mini ImageNet and tiered ImageNet using ResNet 18. Our MixtFSL outperforms the associative alignment in all of the cases. In summary, we introduce a fully differentiable end-to-end representation learning method. We also present a robust 2-stage algorithm for training such a model. Our method achieves the state-of-the-art results on 4 datasets using 4 different backbones. Please visit our project webpage for more information. Thank you for your attention.